So here's the video for lab 1 of Ecen 347, and I'm just going to go through some of the bullet points you have here. So for wave rectification, that is simply just turning an AC source into a DC source by adding some diodes and eventually some capacitors in there. And the result of converting from AC to DC, there tends to be a ripple voltage, and that is due to the fact that the AC source isn't always completely 100% converted, and that's why the capacitor has to be added in these things. But this is just part 1. I have the diode and the 1K resistor hooked up, and we got the signal being applied on the anode of that diode there. Both of the grounds are connected, and this is what the original this is what the affected waveform looks like. The channel 2 is the V out that I have connected across from the diode there. So you can see the original signal gets cut off on the negative cycle of the voltage. So in order to smooth out this section right here, that little noise going on, that's why we add the capacitor in there, which is what's going on here. I just place the capacitor in parallel with the resistor, and that will help mitigate that effect there. And for this first part, I chose a 47 micro, which is what the formula turns out to be equaling. The delta V out equals Vm over frequency times resistance times capacitance. So I stuck that in there, and channel 2 is showing what that ripple voltage is going to end up being. That's the V out. So I believe the experiment was to achieve a 20% ripple voltage of the Vm, which would be 10 volts, and that is pretty close to 2 volts there. So I believe I achieved that, and this is just me measuring the voltage of the diode. It came out to be 1.2, which doesn't really make sense. I don't know if it was an oscilloscope issue that I was having. But the experimental value or the theoretical value that I did end up calculating was, I believe, 0.4 volts. If I did get it right. Let's see. Yeah, it was 0.4 volts. So this is just the effect of decreasing the capacitance. This is the 22 microfarad, I believe. And as you can see, the voltage output is at 3 volts, which with smaller capacitances, you're going to have a bigger voltage ripple, just because it's less of a value to mitigate that voltage ripple. And then this is going to be the 100 microfarad, and as you can see, we went from 3 volts, and then we had the 20% ripple, which was about 1.79, and as we keep increasing the capacitance, it keeps going down to a 1.39. So yeah, long story short, the more capacitances you have, the smaller the voltage ripple will be. So this is the second part that we ended up going to. Let's just see here. Bring me back to my points. So, okay, yeah, so this is the full wave rectifier, and this is essentially creating that full, it's rectifying that full signal. So on the positive cycle, it will also get turned into a DC source, and also on the negative cycle. That is the point of having these full wave rectifiers. So yeah, there's the diodes are facing away from each other in this kind of triangular pattern. You can check on my lab report the exact configurations of how these are. You can't really tell too well on these, but you can see that the alligator clip here, that's where the voltage signal is coming from, and this is technically the ground on this side of where the signal is being picked back up, and then you were just probing on each side of those. But essentially what's going on is it's allowing a certain path for the positive voltage cycle to flow through. So it's going to go through the alligator clip and then to the right and then through that resistor and come back down. But on the negative cycle, it will actually go the opposite way through the bottom alligator clip and up to the right and then across the resistor and back up. And the purpose of this is to create a zero or net current of a net current of zero. And this just helps to smooth out and create hopefully a more DC like AC source. So when we go ahead and place a capacitor, it's basically the same story. We just smooth out those ripples a lot, and I can pull up some data here. So yeah, the effect on the second experiment reflected with the same or the first part as well. As we increased the capacitance, the ripple voltage also went down. I guess I can just add on to saying that this last one, this is known as like the simple full wave rectifier. There's definitely more complex versions of this that create a cleaner signal and isn't as crazy as showed in the oscilloscope measurements. I can show you what the other ones look like here. So these are just kind of the part 2 of that full wave rectifier, and we just had to use the difference between the 2 V outs to obtain that. And normally the ripple voltage is the difference between the input and the output, and that's what we're basically calculating here. This Y1 and Y2 is just going to be the difference of those 2 channels there, and that was for that obtaining a 10% ripple value for that part 2, and we're using a 100 microfarad capacitor for that. That's just kind of more of experimentation that I was doing to set it up. Let's see. So yeah, this is our 22 microfarad, so low capacitance means a higher ripple voltage. And yeah, that's pretty much all I can think about saying. I'm not sure if there's anything else that you want me to include in here, but I believe I hit all the points. So thanks.